Hello everyone, my name is Andres Torres. Today I will talk about EMG-based predictions of gait maneuvers for lower leg prosthesis. So we should be able to conceptualize what an ideal prosthetic device does. Ideally, it should predict our intention, or it should perfectly react to biosignals. Surface EMG measures volitional muscle activation from the safety of our skin. We can use these biosignals to estimate the contraction effort of the individual muscles on the leg and use them to classify 5 different types of gait maneuvers. Ideally, this classification should occur during the swing phase leading up to the stance phase or quickly after the heel strike. We should classify these steps early during the gait cycle so we can appropriately move the prosthesis in the correct trajectories. An overview of what will be presented will be data acquisition, data conditioning for feature extraction, and the results from the machine learning classification. Data acquisition was mainly performed by a motion capture system. This motion capture system uses infrared light and reflective markers to determine the position of rigid bodies. It is also connected to a force plate, which we use to measure the ground reaction forces and calculate ankle torque. Finally, everything is also connected to an EMG with 4 channels. 4 EMG sensors were placed on my right leg around the shank, which is the lower part of the leg. The walking experiment was performed on a wooden walkway, where the center blue square is the force plate. If the hypothesis is that we should detect distinctive EMG gait patterns for different gait maneuvers, then we should place the EMG sensors accordingly. A classic example would be the antagonistic contraction between the GA and the TA muscle groups. As shown in the lower left image, to move our foot up and down, we must contract our GA muscle and relax our TA muscle, and vice versa. Similarly, to move our foot side to side, we must control different parts of our GA muscle by relaxing and contracting them. That is why the 4 EMGs are placed, one in my TA muscle group in the front of the shank, one in the center back, right in the center of the GA muscle, one to the right of the GA, and one to the left of the GA. Also, the placement of these sensors are near and or above where you will expect a transtibial amputation. For any classification experiment, we must have a ground truth, which in this case is the type of step maneuver that we are performing. I performed 5 different gait maneuvers: a straight walk, a left turn, a right turn, a step up, and a step down. To efficiently label all of these trajectories, I took the vertical foot displacement and created 2 thresholds, one at the beginning swing phase and one at the ending swing phase. Similarly, the step turn was classified using the shank yaw orientation. The blue trajectories shown include the stepping up and stepping down because they are a type of straight walk. Similarly, the green trajectory from the left-hand plot includes all of the turns because they did not change in vertical height significantly. However, by combining both classifiers, we can obtain a total of 5 states. The signal processing component of this project is very similar to what we encountered in VME 511. First, we acquire the raw EMG data, and we subtract the mean. This creates a zero mean signal. Then, we full wave rectify the signal and pass it through a 5 Hz low-pass filter. In this case, I used a second-order Butterworth filter. The outcome of the previous steps is the linear envelope. It is also good practice to normalize each EMG channel relative to the maximum voluntary muscle contraction for that group. We will be using the normalized linear envelope as our features. This next slide is my favorite because we get to see the trial averaged EMG response for each type of gait maneuver. At first glance, we can see that the EMG responses are quite different for some of the states, especially during the mid-stance phase. However, this is not particularly useful because it will be a bit late to do trajectory correction by the mid-stance. Ideally, we will predict the gait maneuver during the swing phase or quickly after the heel strike. For the machine learning classifiers, we will vary the amount of information being provided, always cutting from the last values. Now we go into the consensus machine learning performance. Our consensus approach is a best out of 3, meaning that if two classifiers agree on the same outcome, then that is the selected outcome. Still, I recorded the individual success of each classifier. The 3 classifiers used were linear support vector machine, linear discriminant, and ensemble subspace discriminant. On the first column, I show what percentage of the gait cycle was used for the classification. On the first row, first column, we see that we used from the previous swing phase until the next swing phase. For the second case, we used the incoming swing phase onto the mid stance. Then for the third case, we used the swing phase onto basically just after the heel strike. And finally, for the fourth case, we used from the swing phase and just before the heel strike. We can clearly see across all classifiers that performance decreases as we decrease the amount of information given as features. Also, our best out of 3 consensus outperforms the individual classifiers. I just wanted to note that PCA was used to explain 99% of the variance. These reduced parameters for each of the cases. And we also used the 5 cross-validation folds in order to prevent overfitting of the data. I think end results were very good, considering that a hypothetical pure randomness classification for 5 states will be 20%. So 65% using only swing phase data and 82% using swing phase and the first quarter of the stance phase is very good. So we can conclude that the EMG-based machine learning classifiers show potential to be used as early predictors for gait maneuvers. The ML consensus approach improved overall classification over individual classifiers, and of course, accuracy dropped as we decreased the EMG dataset. Future work includes increasing the number of steps per subject and the number of subjects. Also, ideally, we should validate our hypotheses with actual prosthesis users, which goes into the limitations of this project where testing was performed on healthy human subjects and the classifiers were not tested across subjects. Thank you very much for listening to my presentation.